My name is Dave Feldman, and it is my privilege to be the director of Water UCI and to welcome all of you to this afternoon's Water UCI Colloquium featuring Professor David Sedlak from the University of California at Berkeley. Before we begin and before I introduce David's talk on the local water transition for California cities, I want to make just a couple of very brief announcements. We have one more colloquium scheduled this spring. That will be on May 17th, which is a Wednesday, and that will be in Bren Hall. And you can go to the Water UCI website, water.uci.edu, for information. Our speaker will be Fred Ajarian, who is a director for the El Toro District Water Board, and he'll be speaking on water structure, California's aging infrastructure. Second announcement I want to make, particular attention to all of our graduate students here at UCI in the audience. We are having this summer our third Summer Field Studies program. It's open to virtually any student, any graduate student, master's or PhD here at UCI, and you'll have the opportunity to go out in the field at various sites and learn how water research is done. The catch, the application deadline is May 1. So pick up some flyers and get your applications in. All right, with that, it is a pleasure to introduce Dr. David Sedlak, again from the University of California at Berkeley. David's research focuses, among other things, on the fate of chemical contaminants, the long-term goal of developing cost-effective, safe, and sustainable systems to manage water resources, and he is particularly interested in the development of local sources of water. His research has addressed water reuse, as well as the treatment and use of urban runoff to contaminated groundwater from contaminated industrial sites. He is also a co-director for Renew It, which is a collaboration between UC Berkeley, Stanford, the Colorado School of Mines, and New Mexico State University. Renew It is an NSF-funded engineering research center, and the acronym stands for Reinventing the Nation's Urban Water Infrastructure. In addition, Professor Sedlak is the Plato Melozimov Professor of Civil and Environmental Engineering at Berkeley and co-director of the Berkeley Water Center. With that, please welcome David Sedlak. Thank you.
Thank you. Thank you, David. Thank you, everyone, for coming out. It's a beautiful day here in Irvine, so I appreciate you sitting indoors in the dark, but I guess it's always a beautiful day in Irvine, so it's not a big sacrifice, and there was free lunch. So I want to start out, when I give talks and I talk about this large concept of reinventing urban water systems, I often talk about the 4 revolutions in water. And the idea behind the revolutions in urban water systems is that we build water systems to serve our needs, and when they can no longer serve our needs, we bump along for a long time trying to fix them, but always seeming to fail. And then we run into something that feels like a real problem, like an emergency, and we fix them in a hurry. So you could look at the times when we had problems of typhoid fever outbreaks, and we came up with the idea of water filtration and chlorination. Or you can look at the period in the 1970s when rivers were catching on fire, and you can see the large investments in urban water infrastructure under the Clean Water Act to make safe our rivers and streams for fishing and swimming. And the premise of a lot of the things I've been doing the past 10 years is that we're on the cusp of another revolution. It's what I call Water 4.0, the 4th revolution in urban water systems, and it tends to happen in places with water shortages. And what I want to do today is I want to show you kind of how this is happening in California and the American West, because we've had this long-term drought and we've had a recognition among our elected officials that the future of our water systems are somewhat uncertain. And I want to show you how it's almost transcended just being a technical or engineering approach and has become more of a political movement and a system that people see as a response to our future water needs. I also, knowing that there are graduate students in the audience, knowing that there are researchers in the audience, I want to show you that there are many opportunities for interesting research within here, and I'll pick some examples out from the research we're doing in the Renew It Engineering Center just to give you some ideas of some of the things that are going on. But don't expect a deep science talk with lots of chemistry and equations and things like that. It's really a big picture talk to motivate this question of how California cities are undergoing a transition from relying upon imported water coming from long distances to a local water supply, and how that's really changing everything. So let's start by just looking a little bit at the imported water supplies that are the basis for California's cities' water system. So you can see here the McCullamy and Hetchetchee systems providing water for the East Bay and Oakland, and the Hetchetchee for San Francisco. The Delta, the Sacramento-San Joaquin Delta, which is providing not only Bay Area cities with water, but Southern California with water. Mono Lake, the Eastern Sierra system for Los Angeles, and of course the Colorado River system coming through Lake Mead. One observation that we can make about these systems is they rely upon surface water, and surface water is something that you don't have a lot of in the bank, so when you have a dry period, you start to worry about it a lot. And all but two of these systems involve, or three of these systems involve a lot of sharing of the water with agriculture, and that becomes a theme of kind of how elected officials are responding to water shortages, because oftentimes the fate of their water is tied up to a larger political issue of how agriculture is using water. So I don't have to tell a California audience where we've been through a long period of drought. Starting in about the year 2007, the water in California has been about half of what we've come to expect. We had a wet year there in 2011, and maybe we're out of that drought now, but it really was about a 10-year drought that we lived through. And that got people thinking about the fact that surface water systems and precipitation-driven systems are highly unreliable when you think about the hydrology that's historically been here in the western United States. And in many ways, it's a good thing that we had this drought of historic proportions, because it's preparing us for a future which will have less water. So this is a figure, have you seen it before?
No.
Okay.
What is that?
This is a figure from the IPCC report in 2013. This is the climate change models, so the consensus models from the IPCC. And what it's showing is the predictions of how runoff and soil moisture are going to change in the period from 2016 to 2035, so the near future. In the RCP 4.5 scenario, this is this kind of intermediate Goldilocks, not too hot, not too cold emission scenario. And what you can see happening here, in particular with soil moisture, is that as the temperature increases, the soil moisture is going to decrease. And so the way you read this figure is that for each degree centigrade of temperature increase, the soil moisture will decrease by about this much. And so you can see around the west and southwest United States, when the temperature rises by 2 degrees, we're going to have an 8 to 10% decrease in soil moisture. And if you have a decrease in soil moisture, that means that less water makes it to your reservoirs, and you need more water to grow your food, and people use more water for landscape irrigation. So we may or may not have more or less precipitation, and atmospheric rivers and El Nino are a hard thing to gauge, but we can say for sure it's going to be hotter, and when it's hotter, less of the water that falls makes it to the reservoirs, and we have a greater demand of water for growing food and keeping our cities green. On top of that, this period from now until the end of the century is going to see the disappearance or near disappearance of our snowpack from the Sierra. And the Sierra Nevada snowpack is responsible for a significant fraction of our annual water storage. And you can see in these scenarios, this is from an old report from the California Energy Commission, but things haven't changed very much. By the time we get to the period from 2070 to 2099, we'll only have either somewhere between 20 and 40% of our snowpack remaining. So good time to get rid of the ski cabin. It's probably going to not be very useful for skiing in the future, but more importantly, we're going to have to replumb our surface water system if we want to capture the water that falls in the mountains, because it won't be held up there as snow, slowly melting it as we need it in the springtime. Now, this is an issue here in California, but it's an issue across the entire American Southwest. This figure shows you the elevation of water in Lake Mead. This is that reservoir just outside of Las Vegas, the one here in the background where you always see the bathtub ring around it as the level in the reservoir falls. And starting at about the year 2000, it's been dropping. And even in the wet winters the past couple of years, it really hasn't risen very much. And you can read hydrology papers and models that say there's going to come a period within the next 30 or 40 years where the water won't be delivered downstream from it because basically all the water will be taken by agricultural water use and this long-term drying trend across the American Southwest. How have cities responded to it? Well, Las Vegas has responded to it with a big infrastructure project. So these are a couple of pictures of what Las Vegas is doing to create their third straw or third drinking water intake, where they're essentially creating the ability with a third drinking water intake to pull water out of the dead pool in the reservoir. That's when you learn about reservoirs, you always learn you're never supposed to suck the water out of the dead pool because that's where all the nasty water is. Well, if the level in Lake Mead is going to fall, Las Vegas wants water, and it's going to get that water by putting the third straw at the bottom and sucking that thing dry. So you can see that's a pretty expensive proposition, $820 million or $0.82 billion, just to adapt for what they expect to be the long-term conditions in the American West. But that's nothing compared to what California is doing. So here is our big infrastructure fix, the water fix, a $23 billion proposal that Governor Brown waxes and wanes hot and cold on. But basically it's this idea of taking what used to be known as the peripheral canals and building a series of tunnels to take water from up north of the delta here in Freeport and sending it underneath the Sacramento-San Joaquin Delta so it can get into the pumps of the state and federal project. And you can see Metropolitan Water has been kind of planning for this to happen by acquiring land in the delta so that it'll make it a little easier for that project to happen. But this is a project that's going to cost us about $1,000 for every Californian, amortized over time. We'll take a big loan for it, just to keep the infrastructure running the way it is. And part of the impetus for this is concerns about sea level rise and the degradation of our infrastructure over time. And so you can see that there's one approach to dealing with a future with less water that involves big infrastructure investments, many billions of dollars being spent to try to get the existing system that we have adapted for a future with less water and more competition for water. So that's kind of the status quo and pushing it as far as it can go. But I think that there's another way to go, and that way, which I think about as a revolution, is kind of a local water revolution. And I find inspiration in this local water revolution from thinking about Singapore. So I don't know how many of you know who this guy was, Lee Kuan Yew. He died, 2 years ago? He was the founder of Singapore, and he had this experience as a young man living in Singapore when the Japanese cut off the water supply, and he recognized how vulnerable his city was to water shortages. And when the British gave Singapore and Malaysia their independence, the Malaysian prime minister, you can see the quote here, felt like he had leverage over Singapore because Malaysia controlled the water supply for Singapore. Here's Singapore here, here's Malaysia around it, here are the Johor Straits here, and this is where the imported water supply came into Singapore. And Lee Kuan Yew, instead of being held hostage by the Malaysians, took up an aggressive project to create a local water supply for Singapore. And by creating a local water supply, he could put the country in a position of better bargaining leverage when it came time to think about renegotiating the water contracts for the imported water system coming into the city. What does this have to do with California? Well, California has elected officials. We don't have dictators yet. And these elected officials are all California mayors in San Diego, San Jose, and Los Angeles, standing in front of their constituents telling them that the future of their city's water supply is a local supply. In San Diego, it might be a desalination plant. In Los Angeles, it might be stormwater capture. And in San Jose, that's an Erlenmeyer flask full of recycled wastewater. So all of these elected officials are saying they would like to invest billions of dollars in doing it a different way, not investing in an imported water supply, not trying to keep these commingled sources that they share with agriculture going and possibly subsidizing the agricultural water interests, because agricultural water interests can't afford these massive projects, but taking their citizens' taxpayer dollars and putting it into local water supplies. And this frees them from a system that they've had for many years that they're starting to doubt will be able to get them through the 21st century. And so what I'd like to do is I'd like to look at these different local water sources, and I think about them the same way that Lee Kuan Yew thought about the 4 taps in Singapore. I think about these 4 local water taps for California cities. Stormwater harvesting, water reuse, water use efficiency. I think about this almost like a virtual tap. That is, if you can decrease the water use, it's like finding water that wasn't there, and then seawater desalination. And I said in the abstract to the talk when I sent this in that Californians don't really like seawater desalination. So I want to talk about our one seawater desalination plant that's operating now. I guess we could talk a little bit more about the ones that have been proposed and that people are starting to build, and why it's a concern for California, and why we might change our opinions about that in the future. So this is the seawater desalination plant in Carlsbad that came online last year. It produces 50 million gallons of water a day, so a substantial amount of water for the city of Carlsbad. And it took a long time to get this built. There was a lot of back and forth, a lot of permitting, a lot of fights between environmentalists and the city, but ultimately it was approved because, probably because of the drought and the politics of that drought period and some creative financing that was done, which is also another story unto itself. But the environmentalist concern about seawater desalination plants included things like it opening up coastal development on the Central Coast, entrainment of fish larvae and young fish into the intake pipes. But most importantly, there was an energy concern. So you can build seawater desalination plant intakes that don't entrain fish. You can solve problems of coastal development with good land use policies, but you can't get away from the fact that desalination of seawater is an energy-intensive process. So this is a bar graph that compares the energy of seawater desalination, about 3.5 kilowatt hours per cubic meter, to the other sources of water that California cities use. So you can see that we already, when we bring water from the State Water Project up and over the Tehachapi Mountains, it's pretty energy intensive. Probably, I mean, this isn't exactly a fair comparison because this is seawater at sea level and this is at the top of the Los Angeles system, but it's on par with what it takes to pump water up and over the Tehachapis. Our groundwater projects are much less energy intensive, and of course, even like the groundwater replenishment project and the West Basin project here are a fraction of the energy involved. So people say, look, why are we going to increase greenhouse gas emissions just to provide ourselves with a water supply? And that is a good question, and I think the Carlsbad plant has had some creative approaches to trying to make it a zero-emission plant by buying green electricity. And when you look at Australia, where they built seawater desalination plants in the last 10 years, they always offset that electricity production with wind farms and solar farms. So you can start to address those issues. But this energy intensity of the process also means that it's an expensive process. So much of the cost of running a seawater desalination plant is the electricity required to force the salt water through the membranes. But it's actually only about like a quarter of the cost. A lot of the cost of a seawater desalination plant is the bond financing of the plant and the operations and permitting of the plant. And this is the missed opportunity. So here's me in the White House last year. That's the executive building, and Barry wasn't home. It wasn't like that. It was the president's science office. And they had this idea with the Department of Energy that they called the pipe parity challenge. So the Carlsbad plant produces water at about $2 a cubic meter. And in Israel, the Sorak plant produces water about 50 cents a cubic meter. And they saw a strategy, much like the strategy that we had pursued for rooftop solar, that dragged down the price of rooftop solar over the past 10 years, to drop the price of seawater desalination by 75%. And after a visit to Israel and discussions with some of the companies out there and some more discussions with people at the DOE, I'm not convinced that we could get 75%, but I bet you we could knock down the cost of seawater desalination. And we can also tie it to our modern grid, which suffers from this problem of the duck curve and kind of the problem of having too much production during the day, and really make a big difference. But this is a missed opportunity, and it's going to go back on the shelf for a while. Hopefully it comes back when saner minds prevail at the Department of Energy. Okay. Stormwater harvesting, this is the next one. And I think this is one that's quite interesting. We already harvest stormwater in California. The Montebello Forebay takes stormwater. There's a whole network of infiltration basins at the foothills of the mountains to the east of Southern California cities. But those are taking stormwater that falls in the mountains and is held behind dams and bringing it in and infiltrating it into the ground. When California mayors talk about stormwater as a drinking water supply, they talk about capturing the water that falls within the city that now we just do our darndest to get out of the city by putting into concrete lined channels and sending out to the ocean so it doesn't flood people. And so if you think about California hydrology and the kind of storms we get in the winter, it's a difficult challenge. The first thought that people had when we kind of started talking about stormwater harvesting as a water supply is to use green infrastructure. So this is a beautiful area, the Elmer Avenue retrofit that LA Department of Water and Power did in the San Fernando Valley, turned a neighborhood which just used to flood and have water running down the gutter into a bioswale that infiltrated water. And you've seen permeable parking lots and rain gardens that people build. But this is a solution that is appropriate in Seattle and Portland and Philadelphia and Milwaukee or something like that. It's not appropriate for California hydrology, at least if you're trying to capture water. If you're trying to catch the first flush and keep some of the contaminants out of the rivers, these make sense, but they're not a water supply problem. A water supply problem requires that you capture a big storm and hold it and then infiltrate it into the ground. And if you think about this, that's something like this, a big basin like this that holds water. And when you look at this analysis that Rich Atwater at the Southern California Water Committee did, that it scales with cost. If you have a small project like a permeable pavement parking lot or a rain barrel or you're harvesting water from your roof, it costs $1,000 or $10,000 an acre foot for that water. So it's more expensive than desalinated seawater. The projects that make sense economically are when you capture a lot of water in one place because you can manage the infrastructure in an appropriate way. And so when Los Angeles started thinking about this problem, they started thinking about projects like this. This is the Rory M. Shaw Wetland Park, really close to the Burbank Airport. And this is the artist's conception of what's going to happen when a Superfund site that was a gravel quarry gets repurposed into a stormwater capture and recharge facility. They're going to take this gravel quarry, they're going to put a liner in it, and they're going to use it to capture all the stormwater that falls in this adjacent neighborhood, which was built at a time when people thought you didn't need storm sewers because it was the valley and the water percolated quickly. But now it doesn't work that way because we've covered a lot of the land with housing and pavement. And so it floods in here every time it rains. So rather than building storm sewers and sending all this water into the LA River, they can capture it here. And since this is in a recharge part of the city, a recharge zone for the city, they can feed it back into the groundwater. And they do that by passing the water through a constructed wetland and then sending it to an infiltration gallery. I was very impressed by this project when I first heard about it. And I said, I want to go see the site where this incredible project's going to happen. And that's what it looks like on Google Maps when you look around the edge of it. Because it's an industrial part of Burbank, a place that doesn't have a lot of parks and recreation, but it has a lot of car reassembly yards and concrete factories and all kinds of things that you expect with an industrial area. And it had very poor water quality. So there was a little bit of a disconnect in this project between the people who thought, we'll capture the stormwater and put it in the ground, and the people who said, I have to deliver drinking water that is protective of human health. And so we got involved in this as Renew It, seeing this as an opportunity to turn a capture and recharge facility into a capture, treat, and recharge facility. So if you could find a way to passively treat the water before it infiltrates into the ground, you can take this winning idea of stormwater capture as a groundwater supply and make it viable. And this is the approach that we're taking, capturing water, putting it through first something called a Minnesota filter, which removes phosphorus, then through a wood chip reactor where you can see denitrification, and then percolating it not through the native rock and sand, but through some geomedia that has been enhanced with biochar and manganese oxide minerals. We can actually absorb metals, remove nutrients, and break down toxic chemicals that might be there. And so this is what our system looks like. The first iteration of this took place in Sonoma. One of our partners is the Sonoma County Water Agency, so we did an experiment there. There are our columns. They're wrapped in foil to keep the light off of them. There are the bark chip reactors. We're doing a larger project like this now adjacent to that site in Los Angeles to try to see how this works. For those of you who are kind of technically oriented in the room, it's kind of been a fun project because we get to try all these different configurations of columns and media, and we get to look at how the microbes affect the biofilms and affect the clogging in the columns and which chemicals are removed. So it's kind of like, for me, who's like more of a techno geek who likes to think about chemistry, this is a wonderful project to work on. And it's even more challenging because it's far away from our lab, so it's all computer controlled, and we have remote monitoring systems so we can tell when the system's functioning properly. I'll just show a little bit of data just to prove to you that this is actual research and we're not making it up. Here's some challenge tests. We put these columns out in the field for an entire season, and then we brought them back to the lab and challenged them with mixtures of different kinds of herbicides like atrazine and diuron, or some chemicals that you might see coming off of the tires of cars like benzotriazole, or this phosphorus-containing flame retardant. And what you can see is the only place where we actually see these compounds is in our controls, where we just have sand. When we have biochar present, or when we have biochar and manganese oxide present, these things are removed, mainly by adsorption, but also partially by biotransformation and chemical reactions. We also are able to remove the metals that you care about, things like lead and cadmium, which maybe are human health concerns. Not as good at removing the copper and the zinc, but these aren't generally real big concerns when it comes to drinking water supplies. They're more of ecological concerns. So that's kind of the story for the idea of stormwater as a drinking water supply. You can take advantage of the fact that enough rainfall falls within California cities to greatly augment your water supply. And then the challenge is finding places to capture and hold on to the water, and now building passive treatment systems to treat the water as it percolates in the aquifer. But I would say that the one that most people are most excited about and that you see the most energy going into in the last few years has been water reuse. Water reuse is the idea that we have all of this water coming out of our sewage treatment plants, and if we send it to the ocean, that's wasted water. We should be able to find a way to repurpose and reuse this water. And of course, we already do this in California. For the last, 100 years, we've been using our wastewater for agriculture. For the last 50 years, we've been using it for landscape irrigation and things like that. I think here on the UCI campus, you have the purple pipes here, and I'm here to tell you that that's not the future. So the idea of taking wastewater effluent and using it on a golf course, or using it to water your plants in the highway median, that just is not going to happen in the future. And I have two reasons for this, and I'll call them the purple pipe problem, because it's got some alliteration in it. This is the city of San Jose. So San Francisco Bay is up here. The wastewater treatment plant for the city of San Jose is here. And San Jose is a big city. It actually annexed its neighbors by telling them they had to join it if they wanted access to the bay for their wastewater discharge. So like the way that Los Angeles annexed its neighbors by providing them with water, like in the movie Chinatown, San Jose did it by giving them access to a sewage discharge point. And what they did at the San Jose wastewater treatment plant in the 1980s is they started building a purple pipeline for reusing their wastewater. And if you see that beautiful new 49ers stadium, the turf is all watered with recycled water and the toilets flush with recycled water. That's up here in this area near Santa Clara. But if they wanted to expand this system to use more than a few % of the city's wastewater, they were going to have to start building great big long lines to get the water to the few places where they could use a lot of it in one place. New housing developments, corporate office parks, and golf courses. And that turned out to be very expensive. So the city didn't want to build a whole new water distribution infrastructure network, and that was one thing against it. And the other thing against it was cross connections. This is a picture of a cross connection between a recycled water pipe and someone's household drinking water supply. Actually, I think it was in Orange County somewhere. So the public health officer showed this to us at an NRC meeting a few years ago, and I kept the slide because it illustrates that we have, when we bring recycled water, which is not intended for drinking water purposes, into residential neighborhoods, the potential for cross connections is actually higher than you would think. So if you're like me and you spend time reading Australian newspapers in your free time, every month or so, there's an Australian school where the custodian or plumber accidentally hooks the purple pipe up to the drinking water fountains, and public people get mad at that. So this has really taken the wind out of the sails of non-potable water reuse, or this idea of taking our wastewater and using it for landscaping. So the alternative is something that we call full advanced treatment, or FAT. Isn't that a great acronym for something that we do with water? We take the wastewater from the sewage treatment plant and we put it through microfiltration and then reverse osmosis. And after reverse osmosis, we put some hydrogen peroxide in and shine some UV light to make hydroxyl radicals. And we're done with it, we put it back in the drinking water supply. And this is the process that was pioneered here in Orange County at Orange County Water District with the groundwater replenishment project. And so this is how the groundwater replenishment system works. So here's the ocean. I guess we're right around here somewhere, right? Here. And the water from the Orange County Sanitation District goes through this full advanced treatment process. About a third of it goes to a group of wells that are a seawater intrusion barrier, and they become the water supply for Huntington Beach, I guess. And then two-thirds of it goes up here to Anaheim and goes in this lake here and then percolates in the ground and becomes a drinking water supply. And this process, I mean, it really is amazing. You're very fortunate to have Orange County Water District near you because they really are an innovator in this area. It's been through all kinds of public health scrutiny, and it's passed with flying colors, and people all around the world want to emulate what Orange County's done with the groundwater replenishment project. But unfortunately, that's just not possible everywhere. And the reason that's not possible is something that I refer to as the location challenge. So here's the city and county of Los Angeles. The city of Los Angeles, their big treatment plant is here, the Hyperion plant by LAX. And their second the treatment plant for the county is here, the Joint Water Pollution Control Plant by Long Beach. It was natural that you'd put the big sewage treatment plants at the end of the pipe, right? So the majority of the sewage for Los Angeles gets treated right next to the ocean, and the place you'd want to put the water back into the aquifer is back here. Place you'd want to use it, because that's where the infiltration zones are, and that's how the system is set up in terms of water supply and distribution. And so we find ourselves here in California at a crossroads. The crossroads is we know we have this great potential for a water supply with recycled water, but we can't get it to where we want to put it. And there are two choices for us at this fork in the road. The first one is something we call direct potable reuse. This idea that we take the water from that advanced treatment plant and we put it back into the drinking water distribution pipes. Rather than what Orange County does, which they put it into the aquifer, and people kind of forget, they lose the connection between the wastewater and the drinking water. But this is like, I'm going to take the sewage treatment plant, hook it up to the water supply. And I think that tends to worry engineers, they're a conservative lot. But the alternative is lots and lots of pipes. And that whole lot of pipe approach seems to be an economic problem. It was the same problem that prevented us from getting excited about non-potable reuse with the purple pipes. So let's see how California cities are responding. Well, with direct potable reuse, the governor asked the state board to do a study to determine whether direct potable reuse was a good idea or not. And National Water Research Institute ran that study. I was part of this expert panel. And this is one quote from the expert panel that really summarizes what we came up with. And it basically says, in kind of, institutionalese, is that it's feasible to develop water recycling criteria for direct potable reuse. And it will be protective for public health. So we said, yeah, this is something that can be done. But if you know anything about like the way the water industry thinks in the United States, we're not a me first industry, we're a me second industry. We want someone else to do it first and make the mistakes and spend the money on consultants and do all the hard work, and then we'll say, oh, it worked? Yeah, we'll build one too. So all the California cities and utilities are waiting for Texas to do it, And in particular, they're waiting for El Paso to do it. So El Paso, Texas is building a direct potable reuse plant with the intention of hooking that treatment plant directly up to their water distribution system. And California utilities and cities are watching that very carefully. But in the meantime, they're still pursuing this idea of lots and lots of pipelines. So this is a proposal that was floated by the Metropolitan Water District back in September of 2015 to take water from the county plant, the Joint Water Pollution Control Plant, and pipe it everywhere and put it, look, you even get some here in Orange County. Isn't that great? They're so generous. They put it everywhere and get it back in the aquifer. And if you know anything about the geography of Los Angeles and you know anything about the traffic patterns, that's digging up a lot of streets where a lot of people live and a lot of cars go, and that's going to be very disruptive. But we're certainly heading that way. And I think the more interesting question is maybe there's a synergy between stormwater capture and recharge and this advanced treatment and groundwater replenishment, because we capture a lot of stormwater already. These are existing spreading basins where we capture the water in the mountains, like I told you about, and we slowly release it from the mountains, and we infiltrate and fill up the aquifer. And these are the locations of the existing and possible water recycling plants. And so if we could use the unused capacity in these infiltration ponds, because after all, we're only infiltrating the water that we can hold in the mountains and the reservoirs from the winter rains, we could use those when they're empty to recharge this water from the advanced treatment system. We might have a way to go. And so my partner at the Renew It Center, Dick Luthi, and his graduate student, John Bradshaw, are looking at this idea of taking water from the Los Angeles city plants like Hyperion and Tillman and Glendale, and seeing what the nearest routes are and how much water could be gotten into the ground by using existing infiltration facilities. And this might drive us to put in more stormwater capture facilities, because they could be used not only when it's raining, but in dry periods to get the highly treated wastewater back into the aquifer. Meanwhile, back up north, we have a little bit of a different problem. So this is Sam Liccardo, the mayor of San Jose, and he's a big advocate for the city of San Jose taking its wastewater effluent and recycling it, giving it off as highly treated water to the Santa Clara Valley Water District, who will probably put it into the aquifer, kind of like a groundwater replenishment project like Orange County. But he's got a problem, and his problem is this. This is where the San Jose treatment plant discharges into Coyote Creek, and this is the Dumbarton Bridge here. So this is a narrow neck in the San Francisco Bay. And this effluent-dominated part of the bay, it's very shallow. And in the summertime, essentially all the water in this part of the bay is wastewater effluent. And so it has no dilution credit for the wastewater outfall. And it's a sensitive ecological area where there's a lot of fish rearing happening. And these are the South Bay salt ponds, which are being restored as ecological habitat. And so if you build an advanced treatment plant, and the Silicon Valley Advanced Water Replenishment Center is the pilot plant for that project, you use reverse osmosis and you produce potable water, and you give that to the water utility and they recharge the aquifer, but you're left behind with an RO concentrate. And that RO concentrate goes into the bay. Now, the salts in that RO concentrate aren't a problem. It's much lower salinity than seawater, but all the stuff that was in the wastewater, the nutrients and the trace organic chemicals and the metals remain. And if you're putting the same mass of those contaminants into the bay in a smaller volume, suddenly you're violating all of your discharge requirements. And so we've partnered with the city of San Jose and the Santa Clara Valley Water District to try to find a way, a cost-effective way of treating that RO concentrate. And we've been studying a process using ozonation followed by open water wetlands to treat this water and remove those contaminants before it goes back into San Francisco Bay. Now, you've probably heard of ozonation, but you've probably never heard of open water wetlands before. And that's a shame, because you have the first open water wetlands in the world close by to you on the Santa Ana River. And so this is a project that we built in collaboration with the Orange County Water District about 5 years ago, where we took part of the Prado wetlands. This is a wetland complex on the Santa Ana River behind the Prado Dam. And we ripped out the existing wetlands and we put in these shallow rectangular basins. And in these shallow rectangular basins, you can see a ground level view here, the sunlight penetrates. And when the sunlight penetrates, the viruses get inactivated, the bacteria get inactivated, and the trace organic chemicals break down from photochemical reactions. And then the nutrients, especially the nitrate in the water, are removed by denitrification in an active biological layer on the bottom. And so anyone who's interested, there are some papers that we published in the last few years about this process. So that's one way in which we can kind of take the water, we can ozonate it to break down some of the chemicals and inactivate the pathogens, and then use the second barrier of the open water wetlands before putting into the bay. We've just built a pilot scale system to study this idea, and we're testing it out over this summer to see if it works. The second approach that we're thinking about for treating this RO concentrate is something that we call the horizontal or living levees. And this is a project that we're also just building at the demonstration scale now. Let me explain it to you. So the idea here is that as the sea level rises in San Francisco Bay, eventually the wastewater infrastructure and the communities in that part of the bay are going to be in danger. And when you think about sea level rise, it's not like the bay is a bathtub that just kind of fills up and eventually floods everyone. It's storm surges that blow over the existing levees that cause the damage that breaks down sewage treatment plants and destroys communities. And so if you can go on the bay side of the levee and put in a narrow wedge of sediment, you can protect the levee from the storm surges by absorbing its energy. And if you can feed that levee with wastewater effluent in the subsurface, you can grow wonderful habitat on here that's very attractive upland habitat for terrestrial ecosystems, and at the same time remove contaminants in the subsurface, because this subsurface will be anoxic and very conducive to denitrification. And in San Francisco Bay, one of the key issues these days is nitrate pollution, because our treatment plants don't remove the nutrients. And so this is the project. We have a demonstration project of the living levee concept. We have a wastewater treatment plant. We nitrify the wastewater. We put it through a conventional surface flow wetland, which also functions as a sanitary sewer overflow. And then we put it through what we call an ecotone slope. That's that subsurface wetland. And here's a picture of it. We had a great time planting it about a year ago. We partnered with an organization called Save the Bay that cultured native plants. And the native plants you can see here, these are the sedges here, and these are the willows here. So we're trying different kinds of ecosystems to see which ones are more effective at removing contaminants. Now the fourth one of these TAPs, or the fourth strategy for urban water systems, is water use efficiency, as I told you before. And so this is a figure from the Pacific Institute. It's again kind of old, but I think I use it as an example to just show you something that I think many of us already know. That is, the majority of the water that people use in their homes is used outdoors. So here are a variety of southwestern and California communities. So here's Irvine Ranch here. Here's Metropolitan and Southern Nevada Water Agency. And what you can see here is that we all use about the same amount of water per person indoors, about 60 gallons per person per day indoors. But we show great variation in the amount of water we use outdoors. And that outdoor water use, as we all learned during the drought, is to keep our gardens going. And we also learned during the drought that we could do well without having the kind of green lawns that our ancestors had back in Ohio. We can have xeriscapes or California-friendly landscaping, or whatever you want to call it, rocks and cactus skulls if you want. We can decrease the outdoor water use considerably by moving away from plain old lawns. So we can certainly reduce our per capita water demand outdoors, and I think in California we kind of did that in the past year, and there are limits to how much we want to do that. I think for aesthetic reasons, for mitigating urban heat island effects, we want to use water in the city. We want shade plants and trees. We don't want to live in a canyon full of rocks. We want some lawns, but we can do better than 100 gallons per person per day, and I think we have in many of our cities. That indoor water part is something that we need to work on. And here, this number, the potential indoor use, 43 gallons per person per day, is a pretty reasonable level. And I think Californians will all be there in a few years because we have these front-loading washing machines and retrofits of those old toilets that are still around that don't have the low flush mechanisms. So we'll be there eventually, but we can go further. And I want to think about how we might go further. So this is a pie chart showing you how we use water indoors. And you can see here this 26% or a quarter from toilets. Obviously, we can decrease that, but not much further. Leaks, about 20%. So these are leaks that happen within our homes that we can take care of. So we can do somewhat better there, but the real opportunities are to make our water systems more efficient with decentralized or distributed water reuse. So this is a figure from a wonderful review article that George Shabanaglos and a colleague of his wrote a couple of years ago, which talks about all the ways in which we can capture water, wastewater, close to the place where it's regenerated and reuse it in a city. So for example, you can build a new housing development and have a community scale treatment system and use that water for the outdoor landscaping. And suddenly that problem, the purple pipe problem, goes away because you don't have to build a great big pipe to send water 60 or 70 miles away where it's reused. You reuse it in your own neighborhood. In cities, you can take the wastewater from a building and reuse it within the building to flush the toilets and do the landscaping. And that's where we really see the opportunity, because in California now, we have a real estate boom in our cities and people are paying crazy amounts of money for apartments in places like San Francisco. And so if it costs a little bit more because they're trying out a new technology, they're not going to notice it. They might even pay a little bit more for it because it's a super green building now. And to show that they were serious about it, when SFPUC redesigned their headquarters building a few years ago, they put in one of these systems themselves. And the system they put in was called a living machine. Any of you ever heard of a living machine? Okay, this is like a wetland, like a little tiny wetland. It's in the entrance atrium of SFPUC. If you ever get to go to the headquarters, check it out. And this is the section that they're watering. And in our Renew It Research Center, my colleague Arpad Horvath and Jen Stokes and Tommy Hendrickson, their graduate student, looked at the greenhouse gas emissions and energy consumption by this on-site water recycling system. And the most interesting finding to me is this one here. This is equivalent CO2 greenhouse gases per million liters of water a day. And what I think is most interesting is that they had this huge greenhouse gas emission, which was more than the greenhouse gas emission of the centralized wastewater treatment system because of a methane emission. So they had a holding tank for the wastewater, and it was sitting there and getting septic, and the bacteria were producing methane, and that was just leaking out of the stack. So talented engineers know how to solve those kinds of problems. We can make these kinds of systems much more efficient. So we can use distributed systems to reduce our water footprint or our water demand indoors. We can use engineering prowess to decrease the greenhouse gas emissions and probably the energy footprint of these things, but we can't take care of the costs. They're still quite expensive. So if you thought about what the most economically efficient thing to do, it would be to build centralized water recycling facilities. And so I guess the last thing I wanted to share with you is this idea that when we think about green infrastructure and cities, if we only count the price of the water, we're never going to go this route of distributed systems. But if we start counting the other societal benefits, things like green jobs and things like reducing urban heat stress or recreational opportunities, suddenly these things become feasible. So this is an analysis that the Philadelphia Water Department did to justify their decision to go the green infrastructure route rather than the gray infrastructure route when they were trying to combat their combined sewer overflow problem. And I'm not saying that this directly transposes to the problem of distributed water recycling systems, but I think when you start to consider resilience in a city, when you start to consider political support, suddenly these things that seem quite expensive seem a little bit more reasonable to do. So in summary, I hope I showed you here in this talk that even though a lot of the momentum is still in the direction of patching up our existing centralized water infrastructure, the elected officials in our state, our community leaders, and increasingly our utility leaders are seeing another way, a way that involves transitioning away from imported water. We could go to seawater desalination, and while a lot of Californians still dismiss it because they remember the bad old days when we were boiling seawater and distilling it, a modern seawater desalination plant, coupled with the kind of things that the Israelis do to pair it with the grid, suddenly starts to look pretty attractive and pretty drought-proof. Water reuse looks very attractive. It looks very attractive here in Orange County. Unfortunately, you've run out of wastewater. There's no more wastewater to recycle here, but Los Angeles has a bunch that they're willing to give you. And so water reuse is going to be an important part of California's future. If we could recycle all of our wastewater, that's about 80% of our indoor water needs. We're going to lose 20% of it because the membranes aren't completely foolproof. We have to waste some through RO concentrate. And we use a lot of water outdoors, but it's a substantial amount of water. Maybe it's 10 or 20% of our water demand could be taken up by water reuse. Water use efficiency, we've gotten pretty good, but as we increase density through smart growth initiatives, as we change our outdoor landscaping, as we did in the current drought, and as we adopt distributed water recycling programs, we can reduce per capita water demand significantly. And finally, this idea of, I was thinking backwards. Stormwater capture, which is what I thought was here, or thought was there, is a viable approach, and we're starting to learn about it now. It's a little bit more susceptible to drought periods. So when it's not raining, your stormwater capture facility is not very interesting. But if you can compare it with the idea of using full advanced treatment and water replenishment with wastewater, you can make these things more economically efficient. And with that, I want to make some acknowledgments. I want to acknowledge the work of my partners in the Renew It Center, especially Dick Luthi, the co-director or director. I'm actually only the deputy director of the center, and a number of our students and postdocs and collaborators. You can look at the Renew It website if you're interested in it. Here are some of the utilities that have funded the work I was talking about today. And if you're interested in learning kind of this whole story about our water systems and the 4 revolutions in water, steal Water 4.0 from a friend or take it out from the library. With that, I look forward to your questions. Thank you very much for your attention. The Israelis do a couple of things that are quite interesting to me. One is that they seriously reduce the construction costs. When we built the plant, I didn't build, when the plant was built in Carlsbad, that high pressure steel that has to get welded is a very expensive operation because of the skill of the union laborers that do it, and it really drives up the cost. And then the permitting in California was much more extensive than it was in Israel. And then the other thing the Israelis do that I find really intriguing is they ramp up and down their rate of production of seawater, and at night they produce more when the power is cheaper. And we don't do that here. Our engineers always say, oh, this can't be done. And so the Israelis figured out how to do it.
So it's not a technological matter?
It's not. Well, they do have something that they do. They don't use microfiltration. They use sand filters before the RO membranes, and they get less fouling and longer run times that way. And I think that's because the sand filters have more biological treatment going on. So there are little tiny tweaks that they make because as an industry matures, the technology gets better and more efficient. They have economies of scale because it's a 120 million gallon a day treatment plant, and they've built like 7 of them. The other thing is they put the water directly into the national water carrier that runs up and down the coast, as opposed to us where each one is like, it's like our nuclear power plant program compared to the French. The French came up with one model there, and us, every single one was a new design challenge, and that greatly increased the cost. So I think that things like that could really make a big difference. That was a good question, though. But that's the last copy. You're going to have to go to the library. Okay, so well, you're right. You're right about that. That when you build a desal plant, the assumptions you make is that it's always going to be needed, and when you turn it off, you still have to pay the bond prices back. And so when it's not running, you're still paying the money you borrowed to build it. And that's a significant amount of money, and that was one of the problems in Australia. But in Perth, where it didn't start raining, they're really happy that they have that desal plant, and they built another one, and now Perth gets a majority of its drinking water from desal. And Israel, something like 90% of the country's drinking water comes from desalination. And so I view desalination as the option of last resort, because if you're really desperate, your city doesn't have to run out of water. You can always build a desal plant, but it's going to be expensive, and it's going to need to run all the time. But all of these projects only make sense if they're running most of the time. And if you think about what I said about the Lee Kuan Yew effect,
I read that recently in Time magazine.
if you see that idea that now California's elected officials can go into negotiations with farmers about water rights, saying, if it costs too much, we know what we can do. And that changes a little bit the dynamic from what it used to be of, well, we're all in the same boat together, we better fix this problem because we need water. And so that's what I think is most interesting about what's happening now. But I don't think desalination has gone away permanently in California, and I could see a point where it gets cheaper and more attractive, and engineers love building big plants, and so that will be part of the motivation for seeing desalination plants proposed over the next 20 years. So they're not going to go away. Well, I'll tell you, I don't fully understand everything about how Orange County works, but the Orange County Water District is a water purveyor, and they do manage the watershed. I think the city of Orange and some of the smaller towns are very focused on stormwater, but they're mainly focused on stormwater for protection of surface water bodies and the coastal discharges to the beaches and things like that. So stormwater harvesting as a water recharge process has not been a big focus, and it's somewhat hard to do in a place like Orange County where the real estate's so expensive. The other one of water use efficiency, you have this structural problem with water utilities that slows down our progress on water use efficiency, and that is the more that consumers conserve water, the less revenue the water utility collects. And water utilities are aware of it, and they try to do the messaging to tell their customers, we're going to ask you to conserve water, and after you conserve water, we're going to raise your water rates. And the customers say, we're going to vote for new directors at the water agency. And so it's a problem, and what you see happening in California is that utilities tend to push water conservation at about the rate of that the population grows. And that kind of balances it out so their revenue stays relatively flat and they don't have to build new projects. But to do the kinds of aggressive things I'm talking about, you need a mayor pushing or a city council pushing. And you need political support and cover for when you raise those water rates, or you have to bond finance them in other ways. Yeah, so there's this wonderful book out called Let There Be Water that came out, I think it's about a year ago, that tells the Israeli water story. And part of it's seawater desalination, and part of it is agricultural water use efficiency. And I think the Israelis can teach us a lot about how to use water more efficiently in agriculture. There's another thing the Israelis do, and they use essentially all of their wastewater for agricultural irrigation. They put it in a national water carrier, and they use it, the purple pipe solution that I told you doesn't work here. You cannot directly transpose the Israeli model to California or other parts of the US. Partly, it's a really tiny place, and so the piping distances aren't such a problem. And also, water is viewed as a national security issue, and it's quite different than California, where we have enough water, unfortunately, for about 100 million people to live here if we didn't do agriculture. So we have like a different political dynamic, a different water rights dynamic, and different geography that I think precludes us adopting the Israeli model of water management, but it's a very intriguing one, and that's a wonderful place to learn about it, that book. Well, so I mentioned that in Australia, the desal plants in Perth gave them an excuse to fund entire solar farms and entire wind farms, and so it's kind of nice that you can kind of have this plan that as you bring in this large energy demand, you bring in a renewable power source and you make it a zero net greenhouse gas emitting plant. But the local desalination issue is kind of hard because it would only be for people who live right next to the ocean, and all of these other, the infrastructure issues get to be very, very difficult. So I don't foresee a time when we have like household scale seawater desalination plants. There might be a time when we have household scale brackish water treatment plants, because oftentimes people either have water table water, shallow water that's not protected in an aquifer, or brackish groundwater under their home that they could exploit if they had a desalination membrane. First of all, if you want an advocate of peak phosphorus, don't come to me. because I think everything that I'm able to read about peak phosphorus is it's something like between, 80 and 200 years away. And I'm like thinking, man, if we could make it through the next 4 years, we're golden. And in the next 20 or 30 years with climate change. And so to me, peak phosphorus is not that big a motivation. I suspect that if you extrapolate the rate of technological innovation, we could probably pull, in 80 or 100 years from now, we could probably pull enough phosphorus out of the ocean to run our agriculture. I mean, that's being a little facetious, but I do think it's not the biggest thing in my mind. And what works against phosphorus recovery from wastewater in developed countries, it's just too cheap. So there are some developing countries where phosphorus costs are relatively high and where you have like night soil collection or sanitation, and it can be used to underwrite a sanitation program. So if you're in a rural village in Africa, it makes a lot of sense to think about recovering phosphorus and nitrogen from human wastes and using that to fund a sanitation program. But in large cities in developed countries, I'm just not seeing it. And part of the reason also is that the phosphorus might be contaminated with things like cadmium or trace organic chemicals, and it's just too cheap on the global market. So sorry, I didn't mean to deflate your sales, but if I was going to put my effort into phosphorus recovery, it would be tied to sanitation as a way to underwrite the costs of running sanitation programs in developing countries. So when I went through these last four, I remember thinking about this at one point, and if you're really ambitious and optimistic and willing to spend money, it's 100%. I mean, but I don't see that water disappearing immediately. So for example, Los Angeles is always going to have that Eastern Sierra water supply and is always going to have some allocation out of the Colorado. And so wouldn't it be nice that in times of drought or in times when they lose the political fight for water, they have an option other than continuing to fight. And so I see it as kind of something that you open up those taps to different levels to diversify your water portfolio. But I would never bail out of the existing imported water system that our grandparents built for us.
So does that mean you support the Cal Water Fix then?
I'm agnostic about it. I see that cities have an option to walk away from the table, and I think that's what's different. And I think in the past they really didn't quite have that option to walk away, and so it changes the dynamic of who would pay for it. And right now the way it looks is like no one's going to do anything during the remainder of Brown's time. And then the question is, who's the next governor, and if they think it's worth spending political capital on. And I'm just not seeing it now that the drought's over. So, the clock's ticking, and eventually the Delta Islands are going to undergo a catastrophic failure, and the problem will solve itself. And so, I don't know, if I were a betting man, Jim, I'd probably the same place I am. See, I see that as we're moving to drip irrigation quite well. Farmers are logical creatures. They're smart people. They're maximizing the amount of crop per drop. And so when they're putting in drip irrigation now, they're putting them in walnut groves and pistachios and almonds and whatever else you want to rag on. So high-value crops can support drip irrigation. But the field crops that they used to flood irrigate and broadcast irrigate, it's not profitable to put in drip irrigation. And so you can imagine a point where we grow only fruits and nuts and marijuana in California because they're high-value crops. And we don't grow hay and rice and cotton and even some of the fruits and vegetables that we grow now. But it's not simply a question of drip irrigation. It's crop selection, and farmers, if they save water by putting in more efficient irrigation, it doesn't mean they're going to return the water to the environment or to cities. They're probably going to try to repurpose that water to grow even more food. And so it's a water rights negotiation and kind of facilitating water markets and making it possible for cities to live with agriculture, because I think there's also a cultural reason for growing food in our state that transcends the pure economics, and kind of finding a way to all live together, perhaps with less agriculture, but high-value crops. And I think the other thing that's happening at the same time is that agriculture that is labor-intensive will probably start going away. So it may be that we go to crops that can be mechanized better, and those crops will be high-value crops and may consume less water. So there's kind of a labor issue here, and there's a water rights issue that is much more complicated than simply drip irrigation. I think the reason I had the pictures of the three mayors there, and if I had time, I'd probably work in a picture of Jerry and Felicia Marcus. I think it's elected officials and the public that drives the utilities. I think a utility manager is constrained by their job, which is kind of keep the rates low, keep the water flowing. The innovation comes from political leadership that supports these things. So I think our engineers are excited to do these kinds of projects and willing. It's bringing the public along and the elected officials. And that's why I think that telling this story to the public and communicating with elected officials is so important, because they open up the possibilities to take risks and to be covered when they fail, if they fail. One of my other hats, when you don't have hair, you wear lots of hats. And one of the hats I wear is editor-in-chief of this journal called Environmental Science and Technology. And in January, I wrote an editorial called Making America's Water Infrastructure Great Again. And I saw all the water infrastructure projects that need to get done. And I think there is still a lot of big water infrastructure projects that need to get done. We need to pull lead out of pipes. We need to fix our transportation system with barges down the Mississippi. We need to fix the dead zone in the Gulf of Mexico and agricultural runoff. We need to be ready for droughts and things like that. So there's a role for the federal government, and there are some big projects we have to do that only the federal government could do. But there are also some technologies that only the federal government can do. And I'll give you an example. I write about this in the book, but it's seawater desalination. So we wouldn't be talking about seawater desalination today if John Kennedy didn't fund the Office of Saline Research with the dream of providing desalinated seawater and using it to stop political crises in the Mideast. And it took 40 years from the time that the RO membrane was first discovered at UCLA to the time that seawater desalination plants became cost-effective in California. And that was basic R&D funded by the federal government in a way that only the government can do. So the most disappointing thing about the possible pullback from basic research and development is we won't have anything left in the pipeline. And I think that pipeline of innovation and technology is possibly going to solve these problems. So a lot of these distributed systems I talked about, they need sensors and actuators, and we need to understand biotechnology and develop material science to make these cartoons that I showed you here something that's cost effective. And so I see two roles for the federal government. One, doing the big infrastructure projects that no one else will do or can afford to do, and the other, funding the innovations that lower the ultimate cost of providing sustainable water. So maybe that's a good question to end on. So thank you very much for your attention.